In this video, I'm going to review the law of sines and the law of cosines. So to start off, I'm just going to review a little bit of right angle trigonometry. So given a triangle ABC, I'm going to let angle C be theta. We then know that sine of theta is opposite over hypotenuse, cosine of theta is adjacent over hypotenuse, and tangent of theta is opposite over adjacent. So, given this right angle triangle, we know how to solve for the different angles and sides of it. But what about if we don't have a right angle triangle? What about if we have an acute triangle or an obtuse triangle? So we're going to start with the acute case. So I'm going to look at this triangle ACB, and I'm going to label each of the angles with an uppercase letter, and I'm going to label the side opposite each angle with the corresponding lowercase letter. So given this triangle, we can actually create right angle triangles and then use right angle trig to see if we can find some rule. So I'm going to draw a perpendicular line from angle C down to side little c. So side H hits side C at a 90-degree angle. So now you see we have two right angle triangles. Well, we know how to solve for sides and angles on a right angle triangle. So looking at triangle ACD, sine A is opposite over hypotenuse, which in this case is H divided by B. And by multiplying both sides of the equation by B, that gives us that H equals B sine A. Now for sine B, looking at triangle BDC, we know that sine B is again opposite over hypotenuse, which in this case is H over A, and similarly we can multiply by A, and that gives us that H equals A sine B. Now, since we have two equations for H, we know that they're equal. So we know that B sine A equals A sine B, and then by dividing both sides of this new equation by sine A and by sine B, we get that A divided by sine A equals B divided by sine B. Now, we want to fit C into this equation somehow. So this time I'm going to draw a side from angle A to side A that again hits side A at a 90-degree angle. So now we have, again, two right angle triangles. So looking at sine B, we now know that sine B, which this time has sides C and G. So sine is opposite over hypotenuse. In this case, it's G divided by C. So that gives us that G equals C sine B. And then sine C, which is the triangle that has sides B and G, is going to be G divided by B. And similarly, that gives us that G equals B sine C. Again, we know these are then equal, and dividing by sine C and sine B, we get that B sine B equals C sine C. And so that gives us that B divided by sine B equals C divided by sine C. And since we already proved that A divided by sine A equals B divided by sine B, so we have this theorem. Given any right angle triangle with angles ABC and sides little a, b, and c, we know that A over sine A equals B over sine B equals C over sine C. Now you are wondering, is there a similar law for cosines? And the answer is yes. So looking again at our acute triangle, you might say, okay, well, what's cosine of A and what's cosine of B? Well, cosine of B is adjacent over hypotenuse. However, if we look at the side adjacent to B, it's not currently labeled. We know it's part of side C, but it's not the whole thing. So I'm going to label side DB X, and then since AB is C, that's going to give us that the remaining portion is C minus X. And so now I can write out what cosine of B is. So cosine of B is adjacent over hypotenuse, and that's going to be X over A. So that's looking at triangle BDC. Well, what else do we know? So earlier I mentioned the Pythagorean theorem. So if you look at triangle BDC, we know that h squared plus x squared equals a squared. And then looking at left-hand triangle ADC, you know that h squared plus c minus x quantity squared equals b squared. Well, the first equation, if we subtract x squared from both sides, we get that h squared equals a squared minus x squared. And so I'm just going to plug that into the second equation, which gives us that b squared equals c minus x squared plus a squared minus x squared. Well, multiplying out c minus x quantity squared, we get c squared minus 2cx plus x squared. And now the two x squareds cancel, because we had a plus x squared and a minus x squared. And so we're left with b squared equals a squared plus c squared minus 2cx. Now notice there that I wrote minus 2cx times a divided by a. Well, a over a is just 1. So multiplying 1 doesn't actually change this equation at all. However, we have that cosine of b is x divided by a. So I've sort of incorporated that, because you can note that if we switch the a and the x, we then have that b squared equals a squared plus c squared minus 2ca times x over a. Well, we said that x over a is cosine b, and so now we have this equation. So we know that given any acute triangle with angles a, b, and c, and sides little a, b, and c, we know that b squared equals a squared plus c squared minus 2ac cosine of b. And since we picked angle b arbitrarily, we can also have these other two equations in terms of c and a. Now, the proof we did of these two theorems was using an acute triangle. However, we can also do these same proofs using an obtuse triangle. So instead of drawing the line through the triangle, it's drawn outside of the triangle, but the proof can be done similarly.